Okay, so the first formula that we learned yesterday was for C if you're given in the N and the R. So we said the N's the number on the left, the R is the number on the right. We said the N can never be smaller than the R, right? It can be equal, but it can never be smaller. So if I have C and R, this is the same thing as saying N factorial over N minus R factorial times R factorial. So for number 1, it would be 8 factorial over 8 minus 5, which is 3 factorial times 5 factorial. We're going to break the 8 down until it hits the larger factorial on the bottom, which is that 5. And then break down the 3, the 2, the 1. These cancel. 2 and 3 go into 6, canceling it out, and I get just 56. Andy. You do?
Yeah, same. The number 2 is different.
Okay, what's your number 2 say?
It's write the expansion of the expression.
Oh, so it just doesn't have this?
Yeah.
Does it? Okay, so it'll be 8, 5, 3. Yeah, it's the exact same. Is this your number 2? Oh, no? To the third?
Yeah.
Okay. All right, so when we expand this, remember we have 3 parts. We have the C first. First of all, if this is 3, then that means N is 3, right? And there's going to be how many terms in my answer?
4.
Good. 1 more than the N, so 4 terms. So the first one is C3, 0, and then I'm going to fill in that space. C3, 1, C3, 2, C3, 3. And then we take that first term, which is 2x, and we raise it to the highest exponent, so it would be 2x to the third, and then 1 down each time. 2x to the second, 2x to the first, 2x to the 0. And then we take the second one, negative 3y, and we start that one at 0 and get higher each time. And then C3, 0, we know we have to find these. 3, 0, 3, 1, 3, 2, 3, 3. This is 1 and this is 1. What are the other 2? 3 each, right? Remember, it should be symmetric, okay? It's also that third row on your, fourth row actually, on your Pascal's triangle if you did that. So this becomes 1, this becomes 3, this becomes 3, this becomes 1. And there's plus symbols in between these. So we're not multiplying these together. We're adding those 4 terms together. So C, obviously, this is going to stay 1. This would be 2 to the third, which is 8 times x to the third. And then negative 3y to the 0 makes it just 1. This is 8x to the third. Then I get 3. This would be 4x squared. And that last one, negative 3y to the first. So I have 3 times 4, which is 12, times negative 3 is negative 36 x to the second, y to the first. Then I go to the next one. So I've got the 3 from the C. I've got 2. I've got x to the first. I've got negative 3 squared, which is positive 9, and then y squared. So 3 times 2 is 6, times 9 is 54 x, y to the second. And then the last one, I've got the 1 from the C. I've got 2x to the 0, which becomes just 1. Negative 3 to the third is negative 27, and then y to the third. So this is minus 27y to the third. Questions on that one? How many of you got it right? Okay, not bad. Yeah, okay, so that's your first 6 rows if I count them from top to bottom. But remember, this is technically the 0 row, so I would use this when n is 5. Okay, all right, so then I'm assuming this is the same or different? Different. What is yours? Oh, that's not going to work. 3a plus b 7. Okay, thank you. But then it's a Pascal's triangle, right?
Yeah.
Then says this, right? So if I kept going on that, let's say, because it's n to the 7th, if I kept going, because I can use that to help me. This is the row I would be using, okay? The one that the second number matches the exponent on here. But it says 6 terms, so this one's kind of shorter to just go directly to your term. Remember, it has 3 parts. It would be C, N, R, and then first term to the N minus R, and the second term to the R. So what's our N in this expansion? 7. And if I want the 6th term, what is R? 5. Always one less. So I want to find C5, 7, 5, right? Okay, this would be 0, 1, 2, 3, 4, 5. Okay, but you could have also done it as 7 minus 5, 5, 7, 6, 5, 2, 1, 5. Still get 21. So that's 21. First term. All right, first term, which is 3a to the n minus r, which is squared. Second term is b to the r. So then this becomes 9a squared b to the 5th. And then that's 189a squared b to the 5th. Raise your hand if you got that one right. Good. All right, getting the hang of it, yes? Questions, because today's very different. Yeah.
So for the Pascal triangle, the first one doesn't count as a row?
It's the 0 row.
It's a 0.
It counts as a row if you're physically counting it, because you can't count. Like, so if I say 6 rows, I mean literally count 1, 2, 3, 4, 5, 6.
Thanks.
But the 6th row is not the same thing, because the first row is 0.
Got it.
Yeah. So you just look for the one that matches the n, which is the second number. That's all. R is 1 less than the numbered term they're looking for. So because they asked for the 6th term, R is 5. Okay, this was what I just cropped it out. Which number was this, Emily?
8.
8 from that. Okay, so it says this is the 5th term, which means R is 4. N is 5 because of the 5th power, right? So this would be C, 5, 4, and then 6A to the 5 minus 4, which is 1, and 4B to the 4th. So C, 5, 4, 5 factorial over 1 factorial times 4 factorial. These cancel. It's just 5 times 6 times A times 4 to the 4th, which is 256, right? B to the 4th. This is 30. 256 times 30. Yep.
Why is 6a to the first power?
Because it's n minus r.
Okay.
So if n is 5 and r is 4, it should have been raised to the first. Okay. A5 is called the counting principles. So we're kind of baby stepping our way into some heavier probability. Today we're going to talk about, well, we'll see how far we could get. Talk about at least permutations. Tomorrow we might finish with the combinations, but you're going to see all the different kinds of stuff in here. Okay, so we start with just like your basic counting principle or the simple counting problems, which basically if I was just trying to find the probability and it was simple probability, I put the number of what I'm looking for, however, God bless you, however many there are over the amount of items in the set. And then we're going to start to learn about things like replacement and non-replacement, okay, those kind of things. So if I wanted to know what's the probability of the even number, of picking an even number from 1 to 10, I would count how many numbers there are in the set there. There's 10 numbers in the set. I would count how many of them are even. Okay, so if it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, obviously there's 1, 2, 3, 4, 5 even. It'd be 5 out of 10, which is 1/2. That's your probability of getting an even number between 1 to 10, okay? That's as basic as it gets. And then obviously we start to get a little bit more detailed. So the first thing that we're going to focus on is replacement. Okay, is there replacement in my set or not? A random selection with a fresh set each time is called with replacement. So if I'm pulling a number out of a hat and I replace it, it's a fresh set, right? Everything that was there the first time is still back there the second time. If there's no replacement, if I've taken a number out of the hat and I've kept it, now I've altered my set. So that's the idea behind replacement and without replacement. Anytime it says like a number is randomly generated from, if it's a computer or whatever, you're assuming replacement. So a computer obviously starts with a fresh set every time. All right, so this one says, determine the number of ways in which a computer can randomly generate one or more such integers or pair of integers from 1 through 15. A says an odd integer. So if you need the visual, we're saying from 1 to 15 are the numbers that the computer can actually generate. And the first question is just tell me how many possibilities there are for an odd integer. So this is odd, right? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 possibilities to choose an odd integer. So we're not doing the probability yet. We're just figuring out how many options there are. B says an integer that's divisible by 4. So what numbers up there are divisible by 4?
3.
What numbers?
Oh.
4, 8, and 12. So just 3 options, okay? That's where we're at. Good so far. Example 2 says 8 pieces of paper are numbered from 1 to 8 and placed in a box. One piece of paper is drawn from the box, the numbers written down, and the piece of paper is returned to the box. Then a second piece of paper is drawn from the box and its numbers written down. Finally, the 2 numbers are added together. How many different ways can the sum of 12 be obtained? So again, if you want the visual, there's 8 pieces of paper. 1, 2, 3, 4, 5, 6, 7, 8. If I'm taking out and I'm putting back in, what's that called? Replacement. So that if I did it the second round, there'd be another 1, 2, 3. I should have done it the other order, but each time there's a full set of 1 through 8. So if I take a number and put it back and then take another number, how many options are there to sum to 12? Well, what's one way I could add 12 from these numbers?
8 and 4.
I could do 8 and 4, so I pick 8 the first time and then I pick 4 the second time.
5, 7.
I can pick 5 the first time and 7 the second time. I can pick 6 and 6. Anything else?
7, 5.
What happens if it's switched? Good. 7 and 5. Is that a different way to get it? 4 and 8. 6 and 6 is the same way, right? It's the same way. Yes? I picked the same 6 both times, right? So how many different ways can the sum of 12 be obtained? 5. And notice, remember the words return to box. That's you're saying it's being replaced. Example 3 says a piece of paper, numbered 1 to 8, placed in the box. One piece drawn from the box, the numbers written down. The piece of paper is not returned to the box. Then a second piece of paper is drawn from the box and its numbers written down. Finally, the 2 numbers are added together in how many different ways? So before we said it would be 7 and 5 and 5 and 7. We said 4 and 8 and 8 and 4. I think we did those in opposite order. And then we said 6 and 6. How does that change if they're not replaced? Can't do 6 and 6, right? It's no longer in there, the 6. Does that make sense?
Yes.
So how many ways are there? 4. Yeah.
If you didn't return the thing back to the box, could you not do 5 and 7?
So these are completely separate ones. I took the 5. If I take a 7 first, the 5's still in there to take, right? If I take a 5 first, the 7's still in there to take. It's the second number in each pairing that would be impacted by the non-replacement. Does that make sense?
Yeah.
Okay. All right. Fundamental counting principle says let E1 and E2 be 2 events. So I pull a number and then I pull a number again are 2 events. I grab a rock from the bag. I grab a rock from the bag again. Those are 2 events. The first, and this should be events, E1 can occur M1 different ways. After E1 has occurred, E2 can occur M2 different ways. The number of ways 2 events can occur is the number of ways from the first one times the number of ways from the second one. So this is an event 1 and event 2 can occur, okay? Or event 2 actually can occur. So I roll the dice and I roll an even number. I want to know how many options there are. I roll a dice and I roll a number, I don't know, divisible by 4. Now it's a second event, and if I want to know the possibility of getting either of those, then I would multiply them together. All right, how many different pairs of letters from the English alphabet are possible? So a pair is 2, yes, right? So there's this one and there's this one. How many letters can fill this space? How many letters are in the English alphabet? 26. How many chances can I fill that? How many different letters can I fill that space with? 26. 26, yes? There's 26 letters that can go in that space, right? Only one at a time, yes, but 26 possibilities of letters, yes? So there's 26 options to go in that letter.
Could you use the same letter?
It doesn't say it can't repeat, so you can assume it's the same letter. How many could go in that second one? 26. So to find out how many are possible, I just multiply those 2 together. 676. It is. A lot of them are like that. Part of the challenge of
What is 676 represent?
that's how many different pairs. So you can do A, and I could do B and B, but I could also do A with B, A with C, like all the way through. So there's 26 possibilities for each one. If it said it couldn't repeat, then it'd be 26 times 25. Does that make sense? Yes? So there's a lot of general knowledge you have to know in this section in the next couple of chapters, like how many letters are in an alphabet, how many cards are in a deck. Like, you're going to have to know a deck of cards. When we get there, I'll show you a whole slide. You're going to have to actually study a deck of cards if you hadn't already. It's 52 cards. You've got to know the 4 suits, the colors, all the different things, okay? So if you're not a kid that ever played solitaire or game, like spoons or anything with your friends, maybe the homework tonight is to do that. Yeah. You're gonna know it. You're gonna have to study a deck of cards if you don't know it.
But if we don't know the test,
No. It's part of your bank of not like a standardized test would assume that you know that. Yeah. All right, a combination lock will open in the right choice of 3 numbers from 1 to 30 inclusive is selected. How many different lock combinations are possible? So first of all, what's the word inclusive mean? Including 1 and 30. So if it was non-inclusive, then it wouldn't include 1 and 30. It would be from 2 to 29, right? So if it's 3 numbers, I got to fill this space, I got to fill this space, I got to fill this space. Does it say the numbers can't repeat? No. So how many numbers could go in that first space? There are 30 different numbers that could go in that first space. How many can go in that second one? 30. And how many can go in the last one? 30. 30 times 30 times 30 is?
I think like 2,700. Yeah.
Questions on that one? So you got to pay attention to words like inclusive, or if it said something about the numbers not repeating, then it would be 30, then 29, then 28, right? Okay, we're going to eventually get to stuff with that factorials, but yeah, super fun. All right, example 6 says, in a certain state, each license plate number consists of 2 letters, but followed by a 4-digit number. How many distinct license plate number can be formed? So 2 letters. Here's my A through Z. Here's my A through Z. And then a 4-digit numbers means there's a 4 1-digit number space, right? What are 1-digit numbers?
1 through 9. No, 1 through 9. Or
0 through 9. How many are in that set? 10. So because we started 0, we stop at 9, it's still 10. Does that make sense? All right. How many letters can fill A through Z? 26. God bless you. How many letters can fill the second A through Z? Did it say anything that they couldn't repeat? Nope. Then I get my 10-digit numbers. So how many 1-digit numbers can fill that first one? 10. And doesn't say anything about I can't repeat. What you will see is the first number can't be 0. With like a telephone number, it'll say it can't be 0 or it can't be 9. Something like that. And then you'll eliminate 2 spaces. Does that make sense? So if it said the first letter couldn't be A, now I've got 50 or 25 spots for that first spot. If it said this number, the leading number, can't be 0 or 1, now I only have 8 numbers to choose from that spot. Does that make sense? So you got to be careful because you'll see lots of stuff like that. This is a great standardized test question. Yeah.
Where'd the 10 come from?
There are 10 one-digit numbers, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 can fill that spot.
Okay.
Yep.
Do you only decrease 1 when it tells you like,
If it said it couldn't repeat, you decrease 1, decrease 1, decrease
so
1.
if it said don't include A and then the first one be 25 and
Yes.
then 25? Or
No, if only it says you can only not use A on the first one, then you're only eliminating A from the first one. 26 could still be there for the second one.
Oh.
So sometimes they'll say, like actually there's a rule, right? You can't start your phone number with a 1 or a 0. So the first space is 8 options. Then the rest of them can be anything. So the rest of them can be 10. So this was what, 676, and then 1, 2, 3, 4. And it all stop there, but if you start your homework tonight, it will feel like less tomorrow. If you don't whine to me about how much time you spent on homework tomorrow, because it's going to feel like a lot if you save it all for tomorrow. But you could get a little head start. And then when you get to permutations, you can stop. But
The video, the whole